introduction was fun talk, but it's nice to have fun and see how it has actually progressed and where are all the application areas. So, let us get back to more serious talk. Now, in the serious talk part, we will talk about robot joints, okay. Then we will talk about work volume, then I will talk about very basic elementary kinematics, okay. Then we will proceed forward into forward and inverse kinematics. So, we know that a robot basic structure is something like this, where we have a controller which can be a PC, which can be a microcontroller, which can be a DSP. Then there is the actual mechanical device, which is the robot arm, okay. And then this is controlled essentially from the controller, right. Now, the robot arm is made up of links. So, these are links and links are connected by joints, okay. And we have an end effector, which is the hand, which is called the end effector. So, the end effector can be a gripper like this, 2 fingers, or it can be a tool, for example, spot welding, spray painting. So, the end effector can be a gripper or it can be a tool. Essentially, there are joints, there are links which are connected by joints, and this is the base. Now, in this course, we are assuming that the base does not move, okay, the base is fixed. So, industrial applications, the base does not move, robot does not move, it is fixed in one place, okay, and the arm moves, okay. So, in all of our calculations, whatever we will talk about, it is essentially. So, first let us talk about the different joints that are possible on the links, right. So, the first kind of joint is called the prismatic joint, and you would have studied some of this, but I will go through this in quickly, and we will try and look at the interesting parts, okay, and the parts of research. So, a prismatic joint looks something like this, where we have a rectangular part and there is another rectangular part which is mounted on that, okay. And this can slide up and down on this rectangular part. Now, obviously, the axis it is clear from here that this cannot rotate on that axis, right. This cannot rotate because it is a rectangle on a rectangle, right. So, this has a degree of freedom to move only up and down, and we say that this is a prismatic joint. It has one degree of freedom, which is a translating or prismatic degree of freedom, okay. So, prismatic degree of freedom is the one that can move up and down along this direction, and we say it has degree of freedom 1. So, by degree of freedom we mean an axis, either it can rotate or translate on that axis, okay. This is the meaning of a degree of freedom here. Now, a body in space has how many degrees of freedom? It has 6. A body in free space. What are the 6? It can translate if I have my x, y and z direction, then it can go translate in the 3 directions, x, y, z directions. So, 3 degrees of freedom, and it can rotate about the 3 axis, which is another 3 degrees of freedom. So, it has 6, okay. So, we are not going to confuse this degree of freedom with that degree of freedom, okay, but essentially you can correlate. For example, this can move along one axis in a translating fashion. So, we can call this a degree of freedom, a prismatic degree of freedom, or a translating degree of freedom. It has 1 degree of freedom. This joint is called a prismatic joint. The second kind of joint is called a revolute joint, and the revolute joint is something like this. It is a cylinder mounted on another cylinder. Now, it's very, and there is a stopper in there. So, the stopper in here ensures that this fellow does not move up and down, okay. So, this can rotate about that axis, but it cannot move up and down, okay. So, this degree of freedom is called a revolute degree of freedom. The variable is theta, which is a rotating degree of freedom, and it cannot move up and down. So, this also has degree of freedom 1, okay. So, the prismatic joint has 1, the revolute joint also has 1. In the previous case, the degree of freedom was linear. So, we can say it can move in a linear direction, x, y or z. In this case, it can rotate about an axis, it can rotate about the x, y or z axis, and we call this theta, right. Now, if there is no stopper in there, then this fellow can also move up and down, and it can also rotate, 2 things it can do. So, this kind of a joint is called a cylindrical joint, in which we have a linear degree of freedom, which can go up and down in the x, y or z direction, and it can rotate about that axis. So, it has a linear degree of freedom and a variable which is a theta, so a rotating degree of freedom. This has degrees of freedom 2, and we call this a cylindrical joint. So, the previous one was prismatic, revolute, cylindrical. Now, the third kind of joint is a universal joint, spherical joint. You can call it ball and socket joint, all mean the same thing. It basically means that if we have 3 axes, x, y and z, then it can rotate about x, it can rotate about y, it can rotate about z. So, this is a 3 degree of freedom system, and this is called a spherical joint, right. Now, by connecting these joints, different kind of joints, we can make different kind of robots, right. Now, 99% of the robots are made up of revolute joints, 99.9% robots are made up of revolute joints. And very rarely will you find robots with prismatic joints, except the robots which are doing assembly. For example, robots which do assembly, they normally have one prismatic joint. Because why? Because in assembly you normally move in this direction. Okay. So, different robots can be made by different joints, and those robots will have different names. For example, if you make a robot only with revolute joints, then all joints are revolute. It is called a revolute axis robot. Okay. Now, if you are making a robot, okay, the first thing you have to decide is what is the joint you are going to use. Are you going to use prismatic joint? Are you going to use revolute joint? Are you going to use cylindrical joint? Are you going to use spherical joint? So, out of these three or four joints, which one would you prefer? That is an interesting question. So, you would prefer a joint that has more degrees of freedom, because you can move more. For example, our joint here is a ball and socket joint, and that is why we can move in 3 axes. So, this is my x, y and z. I can rotate about any axis, because this is a ball and socket joint. Whereas in robots, we said 99% robots are revolute joints, not spherical joints. So, what is the problem? We do not know how to make spherical joints. There is some problem somewhere. We would like to have this one, but we can't have it. So, we make with revolute joints. So, what is the problem with this kind of joint? Whereas biological systems, our joints are ball and socket. You look at this joint, they are all ball and socket. Okay. So, which means that biology prefers this kind of joint, but in mechanical systems we prefer the other one. Either we prefer or we cannot make this, either way. Okay. So, what do you think is the problem with this joint?
It has a point contact.
No, it has a surface contact, ball and socket joint. It is rotating about that point, okay, but we can make it. You have ball and socket bearings, you have spherical bearings these days. So, making is not the problem. You can make this and this separately, then you can heat this and then force fit it. The other way is we can cut it and then we can laser weld it. The other way is we can make it even by using rapid prototyping today. Make both of them separately, okay, and then assemble it. So, the problem is not the making, we can make it, but there is a problem in the control. What is the problem in the control? That if you make it, you will not be able to control it. So, what is the problem in the control? So, if we are going to control this using motors, so I put one motor here, one motor there, another motor there, then the 3 shafts of the motor are intersecting at that point. So, if this fellow rotates, it will interfere with that and that. If this rotates, it will interfere with that and that. So, they will all start interfering with one another now. So, you will not be able to control. Okay. So, we can make this joint, but we cannot control it, because the shafts are intersecting. But here we are able to control very nicely, right. So, why are we able to control here? Because there are no motors here. So, what are the actuators here? They are linear actuators. Motor is a rotating actuator, a muscle is a linear actuator, right. So, when this fellow contracts, this fellow just relaxes. So, although it is interfering, but this fellow is relaxing. In a motor you can't do that, right. So, this is one example of how biological joints are better, okay, that the actuation is linear, and we do not have linear actuators. So, obviously, we can't make this, we are always with motors, and if you try and put a motor, it is not going to work. Okay. So, very few robots will have this kind of joint, essentially because there is a control problem. Okay. So, 99% robots are made with revolute joints, and some axis of them could be prismatic. Okay. So, that is the first thing that we look at. Now, the second term that we need to understand is what we call the work volume. So, the work volume is the volume inside which the robot can move its end effector. Okay. So, if I want to perform a task, the task has to be performed inside the work volume. So, because the base is not moving, suppose I have my arm here, okay, I want to pick and place this object from here to here. Okay. This should be inside my work volume. I can't place it outside my reach and say you bring it from there. It can't go there, because the base is not moving, right. So, this volume inside which the end effector can be placed is called the work volume, and different robots would have different work volumes if their joints are different, right. So, the next thing that we need to look at is the work volume of a particular robot. Okay. What does the work volume look like? So, we can make different robots with different joints. So, this is a robot called a Cartesian robot, which is made up of 3 joints which are prismatic, 3 prismatic joints. That means they can move in this direction linearly, this direction, this is the front view or the side view, this is the top view. In the top view, the full base can go up and down. Okay. So, now what would the work volume look like? What is the procedure that we follow to find the work volume? So, we take one joint, let us take this joint, fully extended condition. From here, if this moves backward, it will go till there and it will be a straight line. Okay. So, this joint draws out a straight line in space. Now, this fellow can go from here to here. So, this fellow also can go from here to here. So, it means the straight line is going from here to here, right. So, it says for this is my arm, it can go front and back. So, this from here to here is a straight line. Now, this full arm can go up and down. My hand can't go up and down, it is not a it is not a prismatic joint. Okay. So, the full straight line can go up and down. So, the area in space that we get is a rectangle, okay, or a square. Okay. So, the sides view of the work volume of this two Cartesian joints is essentially a square or a rectangle depending on the dimensions of this and that. If they are equal, then it is a square. If they are unequal, it is a rectangle. Now, if I see the top view of the robot, this is the joint, the top view joint, the base joint. The base can go fully in that direction in a straight line again. Okay. So, if I see the top view from here, it will be a straight line. Okay. So, this fellow can go from this end to that end. So, this straight line can go from here till there, right. So, essentially in the side view it is a rectangle or square, in the top view it is also a rectangle and square. So, if I combine this and that in 3-dimensional space, what will be the shape of the work volume? It will be a cube or a cuboid depending on dimensions. So, a rectangular robot made up, or a Cartesian robot made up of 3 prismatic joints has a work volume which is essentially a cube or a cuboid. Okay. That is clear, right. Now, if we have a cylindrical robot is one which has one cylindrical joint here. Okay. So, a cylindrical joint is this fellow which can rotate, okay, and also come front and can also move up and down, that is cylindrical joint. So, we saw that our cylindrical joint here can move up and down and it can also rotate. So, this joint is a cylindrical joint. So, in this robot, this is a cylindrical joint, it can rotate and it can also come up and down, and it has one prismatic which is this one. Okay. So, it has one prismatic and 2 revolutes, sorry, 2 prismatics and 1 revolute, right. So, now if you draw the work volume of this, procedure is same. This fellow can go front and back. So, essentially from here to here is a straight line. Then this guy can go from there to there, prismatic again. So, this straight line is coming up this way. So, we get this area again which is a rectangle or a square. Now, in the top view, this fellow can move in this direction. So, this is my, if this is my manipulator, if I am seeing from the top view, this can take a sweep like that. Okay. So, this is the top view taking a sweep across from here to here, that is my theta 1. So, 1 revolute, 2 prismatics. So, what is happening is this fellow is getting swept in space like that. Okay. This is my top view. So, if I take the top view of this, it is a line, this line. Now, because it is doing like this line is getting swept like this from here to here. So, if I combine this and that in 3-dimensional space, what is the volume we will get? So, it is a hollow cylinder. Okay. Inside here is going to be hollow and this is the cylindrical region. Okay. That means the robot can go everywhere here, but it cannot go there, right. That is what it means. So, that is the meaning of the word work volume. Now, let us look little bit further into a 2 degree of freedom system. Now, this is a 2 degree of freedom system, okay, planar. Let us assume this can move in a plane only, it cannot rotate. So, in this case, how do we start drawing? Okay. So, how do we start drawing? So, we start drawing this way. This is 2 degrees of freedom. Okay. It can move, this is one axis which is perpendicular to the board, another axis which is perpendicular to the board. So, this can rotate like this can rotate like that. Okay. Let us assume that there is a joint limit of 180 degrees. Let us make that assumption. So, this fellow can go from here to here, this guy can go from here to here, okay, 180 degree limit. Okay. So, how do we start? First we say it is like this. So, similar to my arm, this also has 180 degree limit. Okay. So, first I move this axis, it closes. Okay. So, this fellow closes about this, we get this shape, right. So, it is here, I have closed. The next I move this one from here to here, I get one more, right. Is it okay? So, how do we start? Extreme extended condition. First I actuate this joint, it moves like this, then I move like that. So, I get one arc here and then I get another arc there, right. And the full outer arc, if my arm is like this and I actuate this one, then I get one big arc. So, I get one big arc like that, right. Is it okay? So, this fellow is fully bent this side now. So, it is here. So, if I open this fellow, it will be something like that. Okay. So, it will be a little bit more like that, something like that. Okay. Right. So, let us not worry about this part of it. Okay. So, how do we proceed by drawing? First, it is like this. I move my first one, I get one arc. Then I move the second one, I get my second arc. So, I get one arc, then I get another arc. On the outside, I get one big arc, which is equal to the length of this one plus this one big arc. So, if there are two joints here, then there will be two arcs here. So, if I add another joint there, there will be three arcs here, but the outer arc will always be one. It will be the sum of the link lengths, right? Is it clear? So, this is my work volume for a 2 degree of freedom system. Okay. So, if you look at that, this fellow has 3. Okay. So, there is 1, 2, 3. It has 3 joints, 1, 2, 3, and there is a fourth one which is moving like this in 3-dimensional space. Okay. So, it can also move like this. This is my top view. So, all revolute joints, first revolute, second revolute, third revolute, fourth revolute. Okay. So, the first revolute joint can move like this. So, if I see the top view, it can have an arc like that. Now, in the side view, it is something similar to this. Okay. So, how do we start? Extreme extended condition. The first fellow will go, you will get this. Then the second fellow will go, you will get this. Then the third fellow will go, you will get that. Okay. So, if there are three joints, then you will be getting 3 arcs in there. Outside will be 1 arc. Now, if I combine this one and this one, what will be the shape? It will be spherical. It's a spherical shape, right? So, the previous one was cylindrical. This one is spherical. Okay. Okay, let us draw it again. So, we are here. I make the assumption that there are 2 links. Okay, this is same as our hand. There are 2 links. First, I move this one. So, it closes by 180 degrees. So, I get 1 arc. Okay. Then this fellow has come here now. So, it has come like this. Then I close this one. So, it comes like that. So, I get 1 more arc. Okay. So, this fellow is like this now. Okay. Right. And then when I open it, it will open on this side actually like this. Okay. So, I do not worry too much about this part. I draw my outer one like this. Okay. So, this fellow will actually open like that and come like this. Okay. There will be a semicircle here. Okay. So, let us not worry about this part, let us worry about the general shape. So, the general shape is something like this, okay, something like that, okay. And this is my work volume. So, if I add 1 degree of freedom which can do like this, then this planar surface is getting swept like this in space. So, what is happening is it is becoming a sphere, okay, with this part where you cannot go, okay. This is a dead end, right. So, now the question that comes up is, we have 3 links, okay, this link, this link, this link, or in our case we have 2 links. Okay. What should be the ratio of the links? Okay. We are saying that there are 2 degrees of freedom and it is revolute joint system, okay, but we are not answering the question of what should be the link length. Okay. Say for example, in our hand the link length is here to here and here to here. Okay, there is some ratio there. Similarly, in the leg it is from here to here, here to here, again there is some ratio between the link lengths, right. So, if you are going to answer the question that what should be the link lengths, how would you answer that? You are designing a robot. First thing you have decided there will be revolute joints. Okay. Why revolute joint? Because easy to control, we can put one motor, we can control. Now, what should be the link lengths? That is the next question. How would you decide the question of what should be the link length? So, one way of trying to answer that is you will maximize the work volume, right. We are going to maximize the work volume. So, if this fellow has a particular work volume, then if you maximize the work volume, then I have maximum points where I can reach, right. The objective of a robot is to perform a task, right. So, with that objective, if I maximize my work volume, then I can reach more number of points, right. So, how do we answer that question? Let us look at this and try and answer the question that we have a 2 link system. Let us talk about a 2 link system, it is easier to understand. Okay. So, this is my 2 links. Okay. Let us say that there is no joint limit now, that 180 degree is not there, this can rotate 360, this can also rotate 360. So, the full arm can go like this, that is 360, this fellow cannot go more than 180, but let us assume that this fellow can go 360. Okay. So, 360 degrees here, 360 here. Now, if I draw the work volume, what will be the shape of the work volume? So, the outer one will be a circle like this, right. What about this one? So, this is bending like this and it's coming like that, right. This can rotate 360 degrees, this can also rotate 360 degrees. So, this fellow has come till here and it has gone round like this. So, this full region is the region inside which we can operate our arm. We cannot go in there because that is a dead zone, we cannot go in here, right. So, this is a region where you cannot go, right. This is the region where you can go. So, now when we are saying that we want to optimize L 1 and L 2, we are trying to answer the question, what should be the ratio of L 1 by L 2? So, in your hand, what is the ratio of L 1 and L 2? Maybe you can look at your hand. So, what is this ratio? When how do we try and optimize it? One way of saying it is that we want to maximize this work volume. What is this work volume? It is V 1 minus V 2. Okay. So, if this is my V 1, then this one is equal to L 1 plus L 2. Okay, that is my V 1, right, and this one is my V 2, which is equal to, well, it is not my volume, is this is the radius. This is radius 1, this is radius 2, this is L 1 minus L 2, right, and this volume minus that volume is the actual work volume, right. So, the work volume V is equal to pi by 4 R, let us call it L 1 plus L 2 squared minus pi by 4 L 1 minus L 2 squared, right, right, that is the volume, right. So, this volume is equal to this minus that, right. Okay or not okay? Sorry, it is not volume, it is area. Okay. So, yeah, thank you for correcting me. So, this area, it is not volume, right. So, the area of this will be this minus that, right. Okay. So, the area of this, although I use the word work volume, but the process is the same. So, this area minus that area, this is the area of a circle, this is the area of a smaller circle, right. So, here we have two variables L 1 and L 2, there are two variables, right, but we have one equation, right. So, we cannot do anything about it. So, what do we do is we make L 1 by L 2 equal, make the assumption L 1 by L 2 is equal to A and say L 1 is equal to A times L 2. Right. So, in this equation we have two variables. So, we convert it to one variable. Then what do? We can take the derivative with respect to L 1. So, I convert L 1 to L 2 and then I take the derivative with respect to L 2 and equate it to 0. Okay. Is it okay? I am trying to maximize, right. So, I take the derivative of this with respect to L 2, equate to 0 and then see for what condition of L 1 by L 2. So, essentially for what condition of A this is going to get maximized. Okay. And if you do that, what we will get is A is equal to 1. Okay. So, for A is equal to 1, we will find that if you take the derivative of this dV by dl 2, equate it to 0, okay, and then find for what condition of A this fellow gets maximized, we will find that it gets maximized for A is equal to 1, which means that L 1 is equal to L 2. So, this is the mathematical way of solving. Okay. Can you solve it geometrically? Can you solve this geometrically? This is the mathematical way of solving. Find the area. Okay. So, this is my area. Okay. But what about geometrically? See, irrespective of the ratio of L 1 and L 2, this is always L 1 plus L 2. It has nothing to do with the ratio. Whatever is the ratio of L 1 and L 2, this radius will always be L 1 plus L 2. So, you cannot change this guy, because it is always L 1 plus L 2. You can change this fellow. So, the total area is this minus this, which means if I make this fellow equal to 0, then the area gets maximized. So, when will this fellow become equal to 0? Is equal to L 2. Then this point, when it bends, it will come exactly here and this will become a point, right. So, geometrically also we can say that when L1 is equal to L2, this fellow inside, this circle inside becomes a point, right, and if it becomes a point, then you get maximum area, right. Is it okay? So, this answers the question that what should be the link lengths? The link length should be, they should be equal. So, are they equal in your hand? They are equal. They are equal in your hand. You can measure and see. What about the link length from here to here, here to here? You can measure and see they are equal. They are same. Okay. Because if it were not same, then you will end up with a region like this here where you cannot go. Okay. So, in order to avoid this, this length is equal to that length. So, if you look at any robotic manipulator, okay, you will find that the link lengths are the same. Okay. So, if you look at any robotic manipulator system, we will find that the link lengths are exactly the same. So, if you are designing a robot, please keep this in mind, that the link lengths have to be equal, otherwise you will end up with a region inside where you cannot go, okay, which is a singular region.
So, what if there is more than one link? I mean more than two links.
What if there is more than one two links? So, on the planar case, like for example this guy, so there are 3 links here. Okay. Okay. So, if there are 3 links, then you will have to look at the singularities where it can go, where it cannot go. This is only for 2 degree of freedom system. This is only 2 on the plane. If we add one more, then probably that link that area will go down. Okay. So, if you have more degrees of freedom, then you do not have this internal singular positions. Okay. But it is interesting to note that normally they would have this one, the other fellow will be in this direction. Okay. So, if you look at the structure, then they will not normally have 3 links like this, the way it is shown here. Okay. So, so this gives us the work volume. We are saying work volume. Okay. So, it is actually a work volume which is made up of the side view and the top view. Okay. This is for a Cartesian robot, this is for a cylindrical robot, this is for an articulated robot. Articulated one has 4 degrees of freedom, 4 revolute joints, one for doing this, second fellow is here, third fellow is here, okay, and the fourth fellow is very small, is there, which is drawn here. Okay. The approximate work volumes will look like this. Okay. Now, there are other kinds of robots which have different structures, or they may have revolute with prismatic joints. Such a robot is called a SCARA robot. So, selective compliance assembly robot arm. Okay. So, this fellow is called a SCARA, or a selective compliance assembly robot arm, which is essentially used for assembly. Right. Now, this has 4 degrees of freedom. The first one is revolute, second one is revolute, the third one is prismatic, and the fourth one is revolute again. Okay. It has 4 degrees of freedom. And so, if you see the top view is, this is a revolute joint. So, this is my first revolute joint. So, it can do like this. Okay. So, we have an outer radius and an inner radius. So, if I look at the 2 degree of freedom here, this is my 2 degree of freedom in the top view. So, if I see from the top of this will appear like 1 degree of freedom here, another degree of freedom here, which is exactly this one. Okay. So, when we draw it here, this is 1 revolute degree of freedom, another revolute degree of freedom, and this can rotate like this. Right. Now, in the side view, there is a prismatic joint which can go up and down. So, it is a straight line. Okay. So, this straight line can be moved in this direction. So, what we get is a rectangular area, okay, this area. So, when this straight line is being swept like that in space, okay, in the top view, so what we are getting is this kind of a area which is a rectangular area. So, the side view is rectangular, the top view is cylindrical. So, when I combine this and this, what do we get? In 3 dimensions we get a cylinder, hollow cylinder again, right. Now, we have talked about 3 degree of freedom, 4 degree of freedom. Now, this brings us to the interesting question. So, one interesting question we answered is that what should be the ratio of the link lengths? The link length should be equal, otherwise your work volume will not be maximized. The second is, how many degrees of freedom do you need? For example, I have an object here on the table and I want to pick it up from here and keep it here. Let us take the example of this fellow. I have this one from here, I want to pick it up from here and put it here. How many degrees of freedom is required? Is the question clear? How many degrees of freedom are required to pick up an object from the table, put it somewhere else. I want to design a robot which will simply pick this from here and put it there. How many degrees of freedom are required? 2, 3, 4, 5. Is the question clear? Question is, I want to pick up something from here and keep it there. How many are required? So when we are designing a robot, you are buying a robot for doing a particular task. The first question that would come up is, how many degrees of freedom are you going to have? Okay. So the simplest task is, of course, picking up something from here and putting it there. So how many degrees of freedom are required? 2, 3, 4, 5. So how do you answer this question? So if I look at this as my xy plane, this one is easy to understand. So this is my x, this is my y, and this is my z axis. Okay, so on this one, if you were to see in that direction, this is x, that's y, and that's my z axis. Okay, so 3 translating, right? So if I keep an object here, okay, so I'm keeping it on the xy plane. Okay, so to catch the object anywhere on this xy plane, I need 2 degrees of freedom, because I might have to move in the x and the y. Right? So to place this object anywhere on this xy plane, I need 2 degrees of freedom, which is x and y, the 2 variables. Next, I need to lift it, because I want to take it somewhere. So I need also to move in the z direction. Right? So x, y, and z, and then moving it like this again is either moving in the x and y, x or y, right? And then putting it down is again z. Are you following? So if this is my axis system x, y, and z, then keeping an object somewhere on the xy plane means that I need 2 degrees of freedom to keep it somewhere. Picking it up means I need a third degree of freedom, which is going to take it up. Move it like this is again moving parallel to that xy plane, then keeping it down is in z. So 3 x, y, z. Is that enough, or do you need one more? Is that enough? Grip means? So open close of this is not a degree of freedom. It is just open close, right? So what would be the other degree of freedom? Now to catch this fellow, I have to orient my hand properly, okay, because this fellow has some shape. So in order to catch it, if I have 2 fingers like that, it should be properly oriented so that I can go and catch it. So which means that I need x, y, z, plus I need one for orientation, right? The orientation is required, because this fellow could have any orientation. So to orient it properly, I need to have an orientational degree of freedom, then to catch it, and then to move. So the total degree of freedom is 4. So you cannot do a task normally less than 4. So most robots you will see have minimum of 4, 4, 5, and then 6. Okay. So minimum degrees of freedom are 4 that are required for lifting it, simply lifting an object, putting it somewhere else. Okay. So what are the 4 degrees of freedom? Moving in x, y, and z direction, and one fellow for orienting. So you can find that there is one fellow, last fellow for orienting. These 2 are for moving in x, y. That fellow is for moving up and down. Okay. So this robot is used is called SCARA robot, Selective Compliance Assembly Robot Arm, and is used for assembly. So today almost all assembly that is done for electronics, for example your PCs, laptops, mobile phones, cameras, all electronic assembly is done by robot. Human beings don't do or cannot do. They cannot do because the chips are so small, and if you see the chips, the legs are even smaller. Okay. The chip is small and it has all kind of legs, and the legs are all straight lines, and they are even thinner than that. So if there is little bit of misorientation when you are going to assemble, the chip will break, okay, or it will jam, something will happen. So human beings don't do this kind of assembly anymore. So this assembly is done by robots, and this is the robot that does the electronic assembly. So 90% electronic assembly for electronic components is done by the SCARA robot, and that is why it is called Selective Compliance Assembly Robot Arm, used for doing electronic assembly mainly. Now why the structure is like this? Revolute. Prismatic is essentially for moving up and down, right? So it can move up, it can move down, and it can move up and down in a straight line. Why straight line? Because the chip assembly has to be in a straight line. You cannot assemble a chip at an angle, the leg will break. Okay. So those legs are very thin and they are straight. So, when you assemble, they have to go exactly in the location and go down straight, otherwise it will break. Okay. And there are many robots. If you look at, there are a lot of videos on YouTube and others for electronic assembly. There will be 3-4 of these robots working simultaneously. Okay. So, one motherboard is assembled in a few seconds. Okay. Less than a minute they can assemble one. Okay. So, there are 6 robots working together. Okay. Each one assembling chips. They can do it very, very quickly. And all the robots have this structure. Something to remember is that if you want motion in a straight line, then you must have one prismatic axis, otherwise you will not get. So, if you are trying to do this with a revolute axis, why? Probably Dr. Dasgupta, when he talks in the afternoon today, because there are mapping between revolute space and Cartesian space is not 1:1. Okay. So, if you are trying to follow a straight line in space, is actually very difficult with a revolute joint robot. Okay. Okay. So, here we try to answer the question of how many degrees of freedom are required for a task. So, before you talk about a task, you have to first figure out how many degrees of freedom are required. For example, if you are trying to do welding, we are doing a welding. Okay. How many degrees of freedom would be required? Or you are doing painting. In the automobile industry, robots do spray painting, okay, welding. Okay. How many degrees of freedom is required for spray painting? So, they take a spray painter and they just follow this kind of motion. Okay. So, how many degrees of freedom are required? But please think about it. Okay. How many are required? Okay. Because it might have to have some angle also. So, picking up an object does not have angle, but if you are doing spray painting or welding, then you might need to go at an angle also. Okay. So, when we are picking up and putting up this object did not have an angle, it was just lying flat there. Now, if I put an angle on that fellow, then I am making it more difficult. Okay. So, for welding and spray painting you need 5, normally. So, industrial robots normally have 5. Which degree of freedom do not you need? Orientation you do not need, the last orientation. Why? Because if you have a spot welding electrode like this, you do not need to rotate the electrode about its own axis, you do not need to do that. Okay. Similarly, when you are doing spray painting, there is no pointing in rotating like this, it does not mean anything. So, you may need to rotate it like this, but not about its own axis. So, x, y, z, rotation about this axis, but not its own axis. Okay. So, one axis is less. So, 5. So, why it is important? Because if one axis is less, then the cost comes down. Okay. So, you should always use the minimum number of axes. Okay. So, it is either 4 or it is 5, rarely it is 6 and very rarely it is above 6, so 7, 8, okay, even more rarely. So, we are having the first question we answered, how many degrees of freedom are required for a task, and we said that 4 is required. If you want to go higher than 4, then it is 5, and then 6 is more general. Link lengths, okay, we have seen the link length should be equal. Why? If they are equal, then your work volume is maximized. Otherwise, you will end up with a region in space where the robot cannot go, which is called a singular region. Okay. So, we have answered these questions. Now, let us move on a little bit more to the concept of transformations. Now, it is a little bit of mathematics, very basic mathematics which is required, but it is required anyway for doing forward kinematics, inverse kinematics. So, if you are looking at a robot structure like this, okay, the base is not moving and the joints are moving. So, what we need to know is what is the coordinate of that end effector with respect to the base is not moving. Okay. So, this is given as 0, 0, 0, and we need to find the coordinate of this end effector with respect to that 0, 0, 0. So, it basically means we need to have transformation matrices that will take us from here to here, here to here, there, there, and then there. So, I need the relationship between this position orientation of the end effector with respect to the base, right. So, we need to know how do we get from here to there. So, let us move on to that. That involves a little bit of transformations, 2 basic transformations which we will cover, and then we will move on to forward and inverse kinematics. Okay. So, let us have a look at this discussion here. So, we have a robotic end effector. Okay. I want to go to this. So, there is a table, okay, and we have kept a part on the table. Okay. So, this part is kept on the table, the robotic end effector has to go and catch that. Okay. What is the fundamental problem? So, how do we pose the problem? So, this is my end effector base, which is 0 0 0, which does not move, right. So, we know how to go from here to here because the link length is known, then we can go from here to here. So, we can go from here to here, right. So, that means I know this vector which is here to here, I know this vector. Next, if I keep it on a table, I must also know the relationship between the robot base and that table. Okay, I must know that distance. Okay. Then on the table where this fellow is kept, I also need to know that. So, I need to know this, I need to know that, and I also know this. So, what is not known is this one. Okay. So, this is the fellow that is not known. Okay, this vector is not known, right. So, I need to know transformation matrices that will take me from here to here, here to here, here to here, here to there. Then I know this vector, I can get these distances from here to here, here to here, then I know this vector. Okay. What I do not know is this one. So, can I find this out? Yes, because this plus that is equal to that, right. So, if I know this and that, then I can find that out, right. So, I can find this vector out if I know this vector, this and that. Now, the whole idea of control is, suppose I want to go to this point, the controller essentially will take the manipulator end effector from here to there. That is the question of control. Okay. Now, and what is inverse kinematics? That means, to go from here to here, I must know what is the position orientation of that point. Okay. So, I need to do the inverse kinematics and figure out that what is the corresponding joint angles which will take me there. So, in kinematics we look at the transformation from this to this to this to that, right. And in control basically we try and find out what is this vector and how to close this vector and take it from here to here. Okay. So, that is the question of control. In kinematics we go in this direction, forward kinematics. If I go backward, then I go inverse kinematics. Okay. So, let us look at how do I go from one joint to another joint. So, the first thing that we need to do is we need to assign frames. Okay. And how do we assign frames? Frames or axis in space. So, we assign frames by saying my z axis is axis of rotation. Okay. So, this is my axis of rotation. Okay. It can rotate about that, and the x axis can be the axis of along the links. Okay. So, we are assigning axis. Then I am trying to go from one axis to another axis to that axis to that axis, right. That is what we are doing, which basically means multiply the transformations between them. So, if you see the relationship between this frame and that frame, so if this is my x, that is my y, and that is my z, right, x, y and z is outward. So, if you are seeing the relationship between this and that, there are two transformations involved. Number one, this fellow may be rotated by some angle about this frame, and second, this fellow could be translated from here to there. So, there are two transformations involved. One is a rotation and the second is a translation, right. So, if I take these two transformations, one is a rotation and this is a translation, then I can go from any frame to any other frame in space. Now, if I can go in the forward direction, inverse of that is the reverse direction, right. So, what we are trying to do is we are trying to find the relationship between two frames which are rotated and translated. Okay. So, let us start off with rotations first and then we will go to translations. So, let us look at the rotation first. So, if we have two axes, so we have two axes. This is my axis which does not move, this is axis A, this fellow does not move. Okay. So, this is my x, y and this is z, right. This fellow does not move, it is my, let us call it the base frame 0 0 0, this fellow does not move. Now, what is the point in putting a frame which does not move? Because if this fellow starts moving, then we have no reference, right. So, one reference has to be there which is not moving, otherwise there will be trouble, right. So, this fellow does not move, my frame A which is not moving. Now, initially let us say this frame which has rotated by some angle was initially the same frame, it was coincident, there was no angle between them. We are trying to find if rotation happens between two frames, what is the relationship. So, first my frame A is reference frame, it does not rotate. Frame B is initially coincident, this is my frame B. Okay. So, initially it is the same frame, this is y, this is x, the red color one, and this is z. Initially they are the same frame, so it is the same. Okay. then I rotate frame B by an angle theta about the z axis. Okay. So, if I rotate frame B by an angle theta, what happens is frame B now is rotated. So, it comes here. So, x dashed, this is y dashed, and z remains the same. So, in this case this fellow has been rotated by an angle theta. Okay. So, we are trying to see the rotation transformation. So, initially they were the same axis, then I rotated B by an angle theta about the z axis. So, this fellow has come here now. Now, the question is, suppose we have a point here which has coordinates B p, which is given by u v w. I want to find what is A p. Okay. What is the meaning of this? The general convention used is P is a point, it is expressed in frame B, its coordinate is u v w, right. Now, what is that corresponding coordinate in frame A? That is what I need to find. So, for every frame which has gone around in space, I need to find what is its coordinate in the reference frame. Okay. Now, what is the meaning of u v w? You will be knowing from coordinate geometry that this is u, that is v, and this is w. So, this is my u distance, right. This is my distance v, that is my distance w, that is the meaning of coordinate, right, and it is expressed in frame B, which is u v w. What is the meaning of x y z? It means the distance again in this frame. So, x is here, right, x, y, and z is that side. This is the meaning, right. So, I need to find what is the relationship between this frame and that frame now, right. So, geometrically can we find the relationship between these two? Okay. So, I make a very small construction. So, I make a construction here and a construction here, okay. And if this is rotated by theta, then there is also theta. Okay. So, what is x equal to? X is this distance. What is equal to in terms of frame B? Then x is equal to u cos theta, which is this much, minus v sin theta, which is that much. So, x is equal to u cos theta minus v sin theta. I am trying to find relation between two frames now. Okay. So, x is this distance, it is equal to this distance. How much is that distance? U cos theta is that distance, minus this distance, which is equal to v. This is v, right, v sin theta, right. So, my x is equal to u cos theta minus v sin theta, right. I am just writing in short. Okay. So, C stands for cos theta, S stands for sin theta. Now, what is y? What is y? Y is this distance. Okay. How much is this distance equal to? Geometrically, this distance is equal to this much plus that much. This is my distance y in frame A, distance from here to here in the y axis. What is it equal to? It is equal to this much. What is this much? Is equal to v cos theta plus u sin theta. So, this much is equal to that much, right, and this much is equal to that much geometrically. Okay. So, geometrically actually I can find a relationship between x, y, z and u v w. Okay. So, cos, right. What will happen to z? Z is equal to w. So, we are trying to find the relationship between the coordinate of a point expressed in frame B in terms of frame A. Okay. If I can do that, then I know what is the rotation matrix or relationship between two frames in space. Okay. These two frames are not translated, the origin is the same. So, how did we start off? We simply said that frame B is exactly same as frame A, then it is rotated by angle theta about the z axis, then my x dash comes here and my y dash goes here, and if there is a point B p which has coordinates u v w, then what is its coordinates expressed in frame A, right. That is what we can say. And then how did we find it? Essentially geometrically we said that this is x. Okay. So, this is x means, and so if this is x, then x, sorry, this is x. So, x is equal to u cos theta, which is this much, minus v sin theta, which is this much. Similarly, y is this distance here, which is equal to this distance, which is v sin theta plus u cos theta. We simply write an equation. Now, if I, and it is rotated about z, so there is no change on z, okay, because it is rotating about z. Now, if I write this in matrix form, then I can write it as x y z is equal to cos theta minus sin theta cos theta 0 0 1 0 0 u v w, right. I have written this in matrix form. It is the same thing, right. Is this clear how this came? Okay. So, it is very simple actually. So, if there is a rotation between two frames, then the relationship between the coordinate of a point expressed in frame B is, which is given by u v w, is equal to the rotation matrix, this one, into its coordinate, which we get it in the reference frame. Now, this matrix is called the rotation matrix. This is a 3 by 3 matrix called the rotation matrix. Okay. That means, if I am given any coordinate in this frame, I simply need to multiply with that rotation matrix and it will come to my reference frame. That means, anywhere in space I can convert from one frame into another, and it is very simple to convert from one frame to another. Now, something interesting about this matrices is that this is a 3 by 3 matrix, right, but 3 by 3 matrix means it has 9 elements, but you do not require 9 elements to specify rotation of an object in space, you need only 3. That is why the other fellows you see this, that are all zeros or ones. Okay. So, basically, although this has 9 elements, you do not require 9 parameters to describe the rotation of a body in space, you need only 3. Okay. So, the other elements of this fellow are, now it has more interesting properties. The interesting properties are that if you look at the mod of the columns, they are equal to, if you look at the mod, there are 3 columns here, right, this and this. What is the mod of the columns? So, the mod is 1, okay, sin squared plus cos squared plus sin squared plus cos squared, and this is 1 anyway. Okay. What is the determinant of this guy? Determinant is also 1. Okay. So, it has some interesting properties. The way we write it is that rotation matrix Z with respect to theta. Okay. So, determinant of this is equal to 1. Okay. So, the determinant of this matrix is 1, and each of the columns, if you call this determinant of the columns is also equal to 1, right. Now, why is the columns determinant equal to 1? Because we are when we said we are choosing our axis like this, it basically means that these are unit vectors or directions in space. This is actually a unit vector, right. What is an axis? An axis is a direction in space, okay, and we have taken it such that this is one unit vector here, this is another unit vector, which are orthogonal to each other. So, when we say I, j, k, that is what we mean. Okay. So, these are unit vectors which are orthogonal to each other in space. So, each of these columns are 1, the determinant is equal to 1, 1 and 1, determinant is equal to 1. Okay. And this matrix is called a proper So, this is a proper orthonormal matrix. Okay. So, this matrix R, the rotation matrix, is a proper orthonormal matrix. Okay. Now, what is the property of an orthonormal matrix? R inverse is equal to R transpose. Okay. So, the property of an orthonormal matrix is this one, proper orthonormal matrix. Okay. So, if you want to find the inverse of this, then it is a question of simply transposing it, finished. Okay. So, the matrix is very simple. Okay. It is just cos sin sin cos, okay, nothing else, rotation about z. Okay. Now, if you look at a very simple case, so if you look at a very simple case, So, if you look at this very simple example, so if we have two frames, frame A is, so frame A is the reference frame, okay, it does not move. Okay. Frame B is rotated by 60 degrees about z axis of A. Okay. It's exactly what I have drawn. Frame A is the reference frame, frame B is rotated by 60 degrees about z axis of A, theta is equal to 60 there. Now, if coordinate of point P in frame B is, so BP, coordinate of my point P in frame B is given by any coordinate, let us call it 2, 2, 2, just for example. Okay. Find AP. Can you do that? Is the question clear first? First of all, there are two frames. The origins are the same. One fellow has been rotated by an axis, by an angle theta, okay, and the coordinate of a point BP UVW is given by the coordinate 2, 2, 2. Just for example, I want to find its coordinate in frame A, because I need to find coordinates in the reference frame always. How do I solve this problem? So, how do we solve this problem? So, I know that BP AP is equal to rotation matrix into BP, right? That is what we just found here. So, this is my AP, this is the rotation matrix, this is BP, right? Right. So, I am given what is BP and I know what is the rotation matrix. The rotation matrix is cos 30, cos 60 minus sin 60, 0, 0, 1. So, this is sin 60, this is cos 60, 0, 0, 1, right. Right. What was BP? It is 2, 2, 2. So, I can find what is AP, right. Very simple, right? Right, whatever is the value, right? It is a very simple problem. So, we can express the coordinate in a rotated system to the reference system, okay. And now suppose we were given, this is let us say part 1. In part 2, suppose we are given AP is equal to 1, 1, 1, find BP. Can you do that? Again simple, right. So, AP is equal to R into BP. So, what we need to do, BP is equal to R inverse equal to transpose BP. Simple, right. That is why that transpose and inverse is important, that you do not have to find the inverse, you can just transpose it. Okay. So, that is why this orthonormal matrix is important, because this fellow is just a transpose. Okay. So, we can go in any direction. Okay. So, now let us look at if we have compound rotations. For example, I rotate about the x axis, about the z axis, then if I rotate about x axis, then what will happen? Okay. I can rotate about any axis, we can have number of rotations also, right. So, essentially we just multiply the matrices. So, this is rotation about z, you can also find rotation about x, you can also find rotation about y in exactly the same procedure. Following the same procedure, we can find rotation about x, y or z. I have done just for z. Okay. So, if you do that, then what happens is, so if you do that, then we can find, we can simply write down r x, r y, sorry, I did find r z. So, it is cos minus sin, sin cos 0, 0, 1, 0, 0, right. Now, if I find R x, can anybody guess? 1 0 0 and R y. So, if you see, there is nothing complex or anything difficult to remember actually, it is very, very simple. They are just 4 terms, cos, sin, sin, cos, nothing else. The rotation, the axis about which it is rotating is 1. This is indicating it is rotating about z. Okay. This will be 0, this will be 0. When it is going about x, then the axis about which it is rotating is 1, this is 0, this is 0, that is 0, 0. This fellow has just changed side. When it is rotating about y, then this fellow is 1. Okay. Those 4 fellows have just changed places. Okay. So, if you just remember that, all this is clear. Now, we are having compound rotations. We have rotated once about I have rotated about the z axis. Now, I am going to rotate about the x axis. I can have compound. Then I can rotate about y also. Okay. So, the thing to remember here is that if you are rotating, we are rotating about the reference axis, not that rotated axis. Okay. So, first rotation is about z, they both are the same, so it does not matter. The second one I am rotating about the x axis. So, if I rotate about x axis, if you can visualize, it is going like this. If you can visualize, this fellow comes here, y double dashed, x double dash comes here, and now z is off, right. So, this is the second rotation, and the rotation of angle, let us call it gamma, about this x axis, right. Now, I can rotate again, I can rotate about the y axis now. So, if I rotate about the y axis, then what will happen? If you can imagine again, it is rotating like that. Okay. Then this fellow is rotating even more. So, this fellow is coming here. So, this is my z 1 2 3 and this fellow has come here, right. Okay. So, I have 3 rotations, first one was about z, then it is about x, then it is about y of the reference system. Okay. Now, I say that the coordinate of this point, this is my point B p, which is expressed in frame B, which has been rotated 2 times or 3 times. What is this coordinate in frame A now? Okay. How do you find that? It is not very difficult. So, we just the rotation matrix about each axis is given here, right. The rotation about z is this one, rotation about x is this one, rotation about y is that one. So, you know the rotations about each matrix, and it has been rotated 2 times or 3 times. So, what we do is we take that order and just we multiply all the matrices. Okay. So, now there is a catch in there. The catch is because these are matrices, okay, we know that matrices do not commute. So, A cross into B is not equal to B into A, right. So, the order in which you are rotating is important here now. Why? Because this rotation matrix is a matrix. So, the order in which you are multiplying is important because these are matrices now, right. So, when you are rotating about the reference system, we pre-multiply. Okay. What does this mean? If I am rotating about theta, okay, which we did here, then I rotated about gamma, then I rotated about alpha. Okay. So, this will be equal to r alpha, r gamma, r theta. So, I am pre-multiplying. Okay. So, we have, if I am rotating about z axis, then about x axis. So, I am first going to multiply x axis, then z axis. So, I am going to pre-multiply, I will not post multiply. Now, the thing to remember here is that we are rotating about reference system. Okay. The rotations took place about the reference system. This is x, y, z, which does not move. That is the reference system, and we are rotating with respect to the reference system. In that case, we pre-multiply matrices. Okay. So, if it is A, then B, then we are going to make it B and then A. Okay. Okay. Does this really happen in the world? So, a lot of these things, as I said in the introductory lecture, robotics is a part of our lives. We may not really think about it, but it is there everywhere, okay, either in shopping or in industrial automation or whatever you are doing. Now, this business of pre-multiplication, does it happen in our really lives, in our daily lives? If you ever think about it, or the reverse question, why does it happen in the first place? Right. So, when you put on your socks, then you put on your shoes. When you reverse it, you take off your your shoes, then you take off your shoes. The process reverses. Do you understand the meaning of this reversal? You put on your maybe banyan, then you put on your shirt. When you reverse it, you take out your shirt, then you take out your banyan. The process reversed, isn't it? The process is reversing. Why does it reverse? Because these are rotations in space. Rotations in space do not commute. The order in which you are going, you have to reverse the order. You cannot undo it otherwise. Why? Because these are rotations in space. So, I am writing mathematics here, okay, some matrices, but in the real world, when I am putting on my socks, you are actually rotating the socks and then putting it in. These are rotations. Then you rotate the shoe and then put it on. But when you are reversing it, what you are doing is you are taking your shoes out, then you are taking out your. So, this what you are doing is this one. Okay. So, if you remember your shoes and socks, then you will never forget this one. Okay. This problem in rotation of matrices is very simple actually. All you have to remember is your shoes and socks, and you will never forget this one. So, be careful that when we are multiplying, we have to pre-multiply matrices. Okay. Then we will get a rotation matrix. And the system that we follow in robotics is this one. We are rotating about the reference system. Why? Because it is easier to understand, to visualize. Okay. So, when I said that we are rotating about this, did you visualize? Actually, it is not that easy to visualize, but it is still okay that okay, maybe if I am rotating here, the axis is moving like this in space. We can still visualize, but nobody stops you from rotating about the rotated system. What I mean by the rotated system is the first rotation is about z, is the same axis. Next, I say, why should I rotate about x? I am going to rotate about that one now. I can do that, right. So, now I rotate about this one. Okay. So, my first rotation was the same. My first rotation was the same about z. Then now, I say I am not going to rotate about the reference one, I am going to rotate about this one. Right. Now, what will happen? Now, if you can imagine we are rotating about B, then what is happening? This fellow will change now, right. So, this fellow will change relative to this. Okay. So, it will come somewhere here, somewhere here, somewhere here. Then if I say I am going to rotate about y, you can rotate about the y also. You can rotate about rotated system. Okay. But then would the coordinates of the point be the same in this system and this system? That is the question. If I am rotating about the reference system, I get this. If I am rotating about the rotated system, then we do not change the order, it remains the same. It remains as r theta, r gamma, r alpha. You do not change the order, it remains in the same order. Why? Because you are playing with the reference system now. Okay? And this is actually more difficult to visualize, because your reference is changing here now. Okay? and this is not normally done. We do not follow this in robotics. Why? Because you can imagine that if there is a frame which is moving in space and you start rotating about that frame, then your reference is gone also. Now there is total chaos. Okay. So, we do not follow this, although you can do it, but if you do this, then your order of matrix multiplication does not change, it remains the same. Okay. Just to remember this and this guy is not done, we follow this only. Okay. Why? Because the reference is not changing here and it is easier to visualize. So, this is the first transformation that we looked at, which is the rotation transformation. Now, we have said that when we are going from one frame to another frame, there can be a rotation and there can also be a translation also. That means, there are two possibilities only. So, let us look at the second transformation, which is the translation transformation. So, the next transformation we are looking at is the translation plus rotation. So, let us look at it and try and understand it this way. So, we have an x, y, z system. So, initially both the frames were the same. Okay. So, this is my frame A, the reference frame A, which does not move. Initially that B fellow was here only. Okay. It was the same frame initially. Then what we say is the B fellow rotates by an angle theta. Okay. It is rotated, and then we translate it and move it forward. Okay. So, first there is a rotation, then there is a translation. So, this fellow origin now goes here, and this is my x, y, and z is somewhere here. Okay. So, this is my x, that is my y, and this is my z. Okay. So, initially they were the same frame, then I rotated one of them. Okay. And this fellow went there. How did it go there? I rotated it and then I translated it. So, now if there is a point B p here, which has coordinates u, v, w, what is the meaning? It means it is this one, right? That is the meaning of B p. So, B p means expressed in frame B, which is this one. So, this is my frame B. Okay. Now, I can see the difference between the origins here. Okay. Right. Is it okay? So, I want to find what is A p, meaning the coordinate of the point P in frame A, which is this distance. I want that one in the x, y, z directions. What I am given is this one B p, which is in that fellow, and I also know the distance between the origins, which is from here to here, and by how much it has rotated. Okay. So, essentially it is saying that this plus that is equal to that vector wise, right. So, if this we call this distance we call A. Okay. So, this distance is called point P is P, A is the frame A, B is the frame B, and ORG is the origin. So, this is essentially the distance between the origins of frame A and frame B. It is a convention of writing it is like this: A, P, B, origin. So, distance between origin of A and B is from here to here. B p means coordinate of point P in frame B, which is that one. What I need to find is A p, which basically means this distance from here to there. How can I get it? This plus that is equal to that. Okay. So, if I write in vector form A p is equal to A p B O R G plus B p, right. Is that correct? Is it correct? Is it correct? Now, something we have to be very careful here, unlike in our normal other courses where frames do not move, here frames are moving in space. So, we cannot write vector equations like that in different frames, because this frame and this frame are two different frames now. So, we cannot add like this, because their frames are different. You can add in the same frame, not in different frames. So, you have to convert this fellow into this, then you can add, right. So, this fellow is rotated by an angle theta. So, if I put a rotation matrix onto this one, then it will get on the same direction as this. So, if I put a rotation matrix here R A to B, now it is okay. Now, B p is in frame A only. Okay. So, if I multiply this fellow with this matrix, then the coordinate of point P is in frame A, right, that is this one, right. So, the moment this is in frame A, this is also in frame A. So, now I can add, right. So, this fellow is this one, right. So, it is expressing B in terms of frame A. So, that is in frame A, this is also in frame A. Now, I can add, now that is correct. Okay. So, if you write this in if I write it in matrix form now, then in matrix form this becomes equal to AP is x, y, z. So, this is x, y, z 1. This fellow has 4 parts. This is 0, 0, 0, this is 1. This is my distance x dashed, y dash, z dashed. This is the rotation matrix. The rotation matrix is same as this. So, this is R A to B. Okay. I am writing it in matrix form. Okay. So, this is my rotation matrix. In this case, we can write this fellow only. Okay. I can just write cos minus sine, sine cos 0, 0, 1, 0, 0. That is for example, because there was only one rotation about z. Sorry, this was rotation about z. So, I have to write it. Okay. Is it okay? So, this is a 4 by 4 matrix, and this matrix is called a homogeneous transformation matrix. This matrix relates the coordinates of a point which is rotated and also translated both. Okay. So, if u v w is on a frame which is rotated and also translated, then what is its coordinate in the reference frame is given by this. Okay. This has 4 parts, and those 4 parts are, this is the rotation part, the rotation matrix 3 by 3, which is same as that. Okay. So, this rotation will be with reference to whichever frame you are on, okay, whether it is x, y or z, the corresponding one will come. This is the distance between the origins. What is that? That is this. So, this part is this part. Okay. So, it is the distance between the origins in the x direction, y direction and z direction. So, whatever is the distance between the origins in the x, y and z, that will come here, x dash, y dash, z dash. This is always 0, 0, 0. This is called the perspective, and this is called the scale. It is always 1. Okay. So, this is called the perspective. This is called scale. This is my rotation matrix. This is called the translation vector. So, if you have 2 rotations, one is, if you have 2 operations, one is a rotation and a translation, then we can go from any frame to any other frame in space simply by using this matrix, which considers the rotation and the translation. Now, this is a 3 by 3 matrix. So, whatever is the rotation vector, it will come in here. This is distance between origins, okay, between the 2 origins. This is 0, 0, 0 always is called perspective, and this is called scale. It is always 1 in robotics. Okay? You are okay? Now, you have used this matrix in while using different kind of software. Can you guess where you have used this matrix? As I said, when you wear shoes and socks, you use that rotation matrix to rotate your shoes or your socks. In the physical world, we do rotations. It is the same thing. Here also, you have used this by using using some computer software. CAD, everybody does not do CAD, right? But something which everybody does. Photoshop, 3D planner. So, everybody does not do 3D planner, I guess. Something which you do, everybody does, it is very common. You do not have to be an engineer to do that. Something where you always do this. What is it that you do? What am I asking? I am saying that you change the rotation and translation of objects. Somebody said it. Yeah, when you zoom in, zoom out. So, when you are using say Microsoft Word, you are zooming in or you are zooming out. When you are using a photo viewer, for example, you are viewing a picture, you can zoom in and zoom out. So, what is it that you are doing? You are basically changing the coordinate of a point expressed in some frame to some other frame. That is what you are doing, right. How do you change it? If you zoom out, then you increase the scale parameter. If I make the scale 2, then all of these coordinates will start getting amplified 2 times. If I make it less than 1, it will start becoming smaller, is not it? So, what is zoom in and zoom out? It is just changing the scale parameter. So, any software that you are using has this zoom in, zoom out, all of them have. So, when you are zooming, what is it that you are doing? The question is, when you are zooming in or zooming out, are you creating another object? No, it is the same one, right. It is the same object which is becoming smaller or becoming bigger. How is it becoming smaller or bigger? Simply by changing that parameter, right. So, in robotics we keep it 1. Why? Otherwise your link will become small or big. It has to be 1. What is the meaning of 1? That it remains 1:1 when you are doing this operation. Otherwise your link will become small or it will become big, which you are doing in zoom actually. So, this thing also we have seen that we do it extensively without worrying about what is actually happening. So, what is happening in zoom in, zoom out is essentially they are using this transformation only. So, they take the coordinate of a point and then multiply it, bring it bigger or make it smaller. Okay. So, it is like saying that if you have the image of a tree. Okay. So, if this is my image of a tree, if I zoom it out, then it will become larger. This coordinate is just going there. Okay. If I make it smaller, it is coming here. This coordinate is just coming here. To us, it is becoming smaller, it is becoming bigger. What is smaller, bigger? It does not mean anything actually. The object is still the same object, it has the same coordinates, only it is getting stretched that side or this side by changing this parameter. Okay. So, this is extensively used. Let us have a look at a very small problem. Okay. So, we have 2 frames A and B. B is rotated by 60 degrees about z of A and translated by say 111 unit in the XYZ directions of A. Okay. So, I hope the question is clear. B is initially coincident. There are 2 frames A and B. A is the reference frame. So, frame B is rotated by 60 degrees about z axis of A, and then it is translated by 111 units in the x, y and z directions of A. So, if coordinate of a point B P is given by 2, 2, 2, find A P. Okay. That is the question. Okay. So, I can actually draw a link here like this and say this is a link. Okay. So, this is my link now. In a real situation, this is a robotic link. Okay. This is a robotic link now, and this fellow has this is my end effector. Okay. So, I am trying to find the coordinate of this point which is expressed in this frame on the reference frame now. Why? Because everything is with reference to the reference. Okay. So, how would I get that? So, essentially I see the relationship between this frame and that frame. This frame has been rotated and translated. So, if any coordinate is given with reference to this frame, I can convert it to frame A by using this one, and that is exactly the question. So, how did we do that? So, AP is equal to homogeneous matrix H or T, or transformation we can call it T, into BP, right. So, what is T? T is this matrix. So, this fellow is my T transformation matrix T, sometimes we call it H. So, this is essentially called a homogeneous transformation matrix. Homogeneous transformation matrix. So, this is a 4 by 4 matrix in homogeneous space that converts the coordinate of a point in a rotated system to the reference system. Okay. So, x y z is equal to how much? Okay, is equal to the matrix. So, this is 0 0 0, this is 1. Okay. This is rotated by z. So, it is cos 60 minus sin 60 0 0 1, it is sin 60 cos 60 0 0 1. Okay. So, the origins have been moved by 1 1 1 unit in the x y z direction. So, this into my coordinate u v w is 2 2 2, right, and then it is just a question of multiplying. Okay. Then it is just a question of multiplying, right. So, if you are given the coordinates in any system which is rotated and translated, we can actually bring it to the reference system simply by multiplying with that, and it is very very easy. Okay. Nothing very intricate about that. Now, the same question comes up that if I am given B p, if I am given A p, how would you find B p? In this case, I gave B p and I said find A p. Now, suppose we give A p and say find B p now, then how would you find out? So, this is equal to A p is equal to T times B p, therefore, B p is equal to transpose. This is not a proper orthonormal matrix. This one is not orthonormal. So, you cannot transpose is not equal to inverse. So, this is not a proper orthonormal matrix. So, you cannot transpose it. It will not be equal to inverse. Okay. But then these are all motions that are going on in space. So, can we look at it, understand the process which actually happened, and then try and figure out what will be the inverse of that. Okay. So, if you think exactly what happened here, okay. So, what happened here is, how did B go there? So, first we rotated A and B were the same axis. Okay. A and B were the same axis. Then B was rotated by an angle theta degrees. So, it went there, that is my x, that is my y. Okay. Then I moved it forward, it went here, that is my b, this is what happened. Okay. So, I first rotated by an angle theta, then I moved the origins by this distance A p O b or g. So, my coordinate of this point B p is here, right, and this is my A p, this is B p. This is how it happened. Okay. And to get this physical process, rotation, translation, we did this and we got this matrix. Now, I am saying that tell me the inverse of this matrix. Okay. I want the inverse. Okay. Can you tell me what is the inverse? This is a physical process. These are all physical processes. So, if I want the inverse of this now, what is the meaning? What is the meaning of forward? Forward means rotate, translate. What is the inverse of that? Rotate, translate backwards. Right? What is the inverse? Inverse means I rotate it by an angle theta this way, reverse of this. It went this side, I want to reverse it. Then I bring it backward. Right? That is the meaning of inverse. That is the meaning of inverse. So, if I were to write the inverse here, first of all, you have to rotate it. So, it is a minus r. Sorry, it is a rotation is an inverse. Rotation is an inverse, which is inverse transpose, right? And I have to move in the negative direction. So, I say minus r into x dashed, y dash, z dashed. Okay. So, I have rotated this fellow and I move it in the reverse direction. Is it okay? Is it okay? So, how did we go there? We rotated and then moved forward. Now, I want to bring it back. That is the meaning of inverse. So, I rotate it, inverse it. So, I have inversed it, R transpose I have inversed it. Okay. So, when I am inversing, this fellow also gets affected. So, which is this R, and then I bring it backward. So, I do minus of this. Minus of this means minus of that. Okay. This fellow does not change, it is called perspective, that fellow does not change, it remains 1. So, the inverse of this matrix is given by, is found this way, in which we find that R transpose, this inverse of the transformation matrix is given by, so this is my R inverse now. Okay. So, rotation, just take the transpose, finished. Then minus of transpose into that will give you the amount by which it has to come backward, and this is my 0 0 0, this is 1. Okay. So, having found that, we can put it in here, okay, and we can solve it, right. Is it okay? So, we can also prove it this way. Okay. So, we can also prove it from here. Okay. We can also prove from here. How can we prove it? A p is equal to minus this one, A p b o r g is equal to this, right. So, I take R inverse this side, which is R transpose, which is equal to B p. This is actually this one. Sorry, there is a minus. Yeah. So, this minus is coming. It is the same thing. Okay. So, we can do it mathematically, and we can also do it geometrically by actually understanding that what actually happened, and inverse, what is the meaning of inverse. Okay. So, if I want to go from one frame to another frame, essentially I need to find the relationship between two frames and multiply them out, and then I can go from one end to the other end. Okay. So, if I am trying to go from one frame to another frame, so if I am going from one frame to another frame, what does it mean? It basically means that if I have one here, okay, I normally put this as my z0, z1, z axis is axis of rotation. So, the general procedure followed is z axis is axis of rotation or translations. Okay. So, I put my z0 is the one which does not move, then the first axis I put it here, this is my second axis z1, this is my third axis z3, so this is my z3. Okay. X axis, the first fellow can go anywhere, x0 is here, it's reference, it does not move. The second x comes along the link, x2 comes here, x3 comes there. Okay. So, z axis is axis of rotation, x axis is shortest distance between z's. Okay. So, this is my distance between the z's, okay. And y axis completes right hand rule. So, if this is my x z, then x will come this sorry, y will come that side. Okay. The y axis just completes right hand rule. So, if z is this side, x is that side, then x, y and z, y will come here. Okay. So, we do not consider y because y has no meaning actually, it just completes the right hand rule. We basically deal with z's and x's only. Okay. So, this fellow completes right hand rule, let us not worry about it. Right. Then what do? We need to find the transformation and rotation between these two frames. Okay. So, the variable here is theta. So, theta is called the link variable or angle between z's. Okay. So, the angle between the z axis is the link variable, sorry, angle between x's. So, when this fellow moves, if you can visualize, this is my theta 1, this is my theta 2, this is theta 2, that is theta 3. So, when it moves, what changes? Theta changes, right. So, after putting the axis notations, we need to find what is the relation between this one and that one. that one and that one frames. Okay, so I can get this as t 0 to 1, this is my t. So 0 to 1 is here, then this one is t 1 to 2, then this one is 2 to 3. Okay. So this is going from 0 to 1, they are the same frame. 1 to 2 is taking you there, which is this one. 2 to 3 is taking you there, which is this one. So if I want to find the relationship between this point and this point, then basically t 0 to end effector, let us say point E, is equal to t 0 to 1, t 1 to 2, and t 2 to 3. So I can go to any other point in space now. Okay. So simply by using this matrix, I can go from the base frame to any other frame, which is like saying that the coordinate, if I know the coordinate of a point on this frame, I can get its reference with reference to the reference frame now, simply by doing this. So I can go basically anywhere. So we started off by saying that if I want to pick up an object like this, I need to know what is this vector. Okay. How do you get that vector? Simply by doing this. So I know this vector. Now this fellow was on a table, I know what is the distance here between the table. So I know this on the table, where is this? I know this. Then I can find that one, right. So if this is my point base, this is my point end effector E. One more frame will come here, okay. One more can come there for the end effector point. So this is my point B, this is my end effector axis E. This point, let us call it conveyor C, this is part P, okay, coordinates I mean. Okay. So I can write this equation. Okay. So B into E, so B transpose E into E of P. So this loop is equal to this loop, right, is equal to transpose of B into C into T of C into P. Have you understood? So I want to find this one. How do I find that? I need this one, this vector. This how do I get? I get it from here. I go from here to here, here to there, then I can go here. I know this one from measurement. I know where the conveyor is, conveyor C. Now on the conveyor, where is the part? I know this also. I must know, otherwise there is no way of catching it. So I know this vector, I know this one, this one. I don't know this one. So what we write is B to E, E to P, which is this one, is equal to B to C, C to P, which is this one. So which is the one that I want? You want E to P. So E to P is here. So how do we get it? E to P is equal to B to E transpose, sorry, inverse into this one, BTC into CTB. Okay. So basically, by using this transformation matrices, we have also gone from here. We can find this vector, and this is the one that the control system needs. Okay. The control system needs this one, because once it has this vector, then it basically has the distances by which it has to go and the angle by which it has to move. Okay. So it automatically can compute the distance and then go there. So the need for this transformation is essentially how to find the relationship between frames, very easy, just by using this. Okay. And just by multiplying it, you can go from any point to any other point. So if some vector is not known, you just write the vector loop closure and then find that corresponding one. Okay. Now in general terms, this is called the distance between, there are 4 parameters. One is called the link length A, which is the distance between z's. Okay, what we need to know. A is the link length. Okay. Then theta is the variable angle, angle between thetas, joint angles. So is the angle between x's, sorry. Okay. Alpha is the angle between z's. Okay. And we have A alpha d is the offset distance, or is the distance between x's. So these 4 parameters are called the DS parameters. Okay. We needn't worry, because it gets pretty mathematical after this. So 12:30 in the afternoon, when you are hungry, is not a good time to do mathematics, but this much is required. Okay. This is the very basis. Okay. So, you should know how to go from one frame to another frame, which is very easy actually, there is nothing difficult here. Okay. So, if you can just know that to go from one frame to another frame, we need this matrix and its inverse of this and this matrix, then you can go from any frame to any other frame. And if you can go from one frame to another frame, you can go anywhere in space. That means I can get this vector, and if you know this vector, then I can basically find that vector, and from control systems basically I need that one. Okay. So, forward kinematics is given your theta, find what is that angle. Inverse kinematics is given that point, find what is the corresponding angle. That is the definition of forward and inverse. Okay. So, let us stop here today, I mean stop here for now.